until fairly recently, it was believed that the atom could not be divided into smaller pieces. We then discovered that there was a definite structure to all atoms that included a solid, positively charged nucleus. Since then, we have found out that some types of atoms have a nucleus that is unstable and can change over time. Inside the nucleus of an atom, we find protons, which have a positive charge, and neutrons, which are neutral in charge. Since these particles are found in the nucleus, we call them nucleons. The properties of an atom are determined by its nucleons. Different elements, and even different atoms of the same element, have different combinations of nucleons in its nucleus. This specific combination of nucleons is given a notation. X is the element, and it is represented by the chemical symbol of the element. A represents the mass number of the element. This is simply the total number of nucleons in the nucleus, and can be found by adding the number of protons to the number of neutrons. Z is the atomic number of the element. This is the number of protons in the nucleus, and is actually what defines the element. For example, if an element has an atomic number of 6, we know that it is carbon. If it has an atomic number of 8, it's oxygen. And finally, N is the number of neutrons in the nucleus. Looking at these, we can write a pretty simple equation that shows the mass number is equal to the atomic number plus the neutron number. If we take an atom of carbon, for example, its notation is 14,6. This is known as carbon-14, and it has a mass number of 14. The C is written in the place of the X to represent that it is carbon, and since that is carbon, its atomic number is always going to be 6. The mass number is 14, meaning that it has 14 total nucleons, or 14 protons and neutrons. Since the mass number represents the number of protons plus neutrons, then the number of neutrons would be 14 minus 6, which is 8. Now, something to keep in mind is that not all atoms are identical, even within a specific element. Carbon can also have a mass number of 12. If we were to write its notation, we would write it as 12,6. 12 is the mass number, so it tells us the number of total nucleons, and since it is still carbon, the atomic number is still 6. To find the number of neutrons, we take the mass number minus the atomic number, or 12 minus 6, to designate 6 neutrons in the atom. While here we show the neutron number, be aware that it is often not included in the atom's notation. A lot of times you will see the notation written with only the mass number and atomic number. So we have one sample of carbon that has a mass number of 12, and another sample of carbon that has a mass number of 14. If we change the number of neutrons in the nucleus of an atom, we say that we have a different isotope of that element. So carbon-12 is an isotope of carbon, and carbon-14 is a different isotope of carbon. Now, atoms are tiny, really, really tiny. So as you might imagine, the parts that make them up are really, really tiny as well. This makes a lot of our conventional methods of measuring them inconvenient. A kilogram is simply too large of a unit to adequately describe the mass of a proton. We can. It is actually 1.660540 times 10 to the negative 27th kilograms. But as you might imagine, someone who's working with these particles on a regular basis might get a bit annoyed with having to do the math with that particular notation. So when we talk about the mass of a nucleon, we say that it has a mass of 1 unified atomic mass unit. This is actually defined as 1/12 of the mass of a carbon-12 atom. We might be tempted to say that this is the average mass of a nucleon, but oddly enough, the numbers don't actually work out that way. The mass of a proton in unified atomic mass units is 1.007276 U, and the mass of a neutron is 1.008664 U. If you do the math, even if we leave out the mass of the electrons, the mass of 6 protons and 6 neutrons average more than the average mass of a nucleon in carbon-12. So if you have 6 protons and 6 neutrons bound together in a carbon nucleus, their total mass will be less than when those same nucleons are apart from one another. For now, we can explain this in terms of Einstein's E equals mc squared equation. If there is less mass, then there is less energy. Nature really likes lower energy states, so those nucleons would prefer to be bound together in that lower energy state rather than apart. Using the mc squared equation, we can determine the amount of energy contained by one mass unit. Mass unit is just that, a measure of mass, so we can plug that into our mass in our equation. Except that finding energy using mass units doesn't really tell us much, so instead we can use the mass of one mass unit in kilograms. Times that by the speed of light squared, and we get 1.49 times 10 to the negative 10 joules of energy. Now remember that a joule is a pretty small unit anyway, so this is not a very convenient way to describe the energy of something. But remember, we do have electron volts at our disposal. There are 1.6022 times 10 to the negative 19th joules in 1 electron volt. So we divide our joules by this and end up with 931,500,000 electron volts of energy in 1 mass unit. Okay, now we have a really big number. This is, however, a bit more manageable as we can rename this 931.5 mega electron volts. Now, mass will sometimes be expressed in terms of mega electron volts when we consider the conservation of mass into energy. Basically, all we are doing is solving for mass. This gives us a unit of mega electron volts over c squared as a new unit for mass.